Linear equations. We're going to learn what a linear equation is, how to solve it. I have my own kind of way of talking about how to solve it. And hopefully that'll make you understand it better. If you have difficulty understanding it right now, I just want you to understand how math works better than just being able to work problems. And so that's what I try to teach. And that's the same way I'm going to try to teach linear equations. So we're only talking about in one variable, of course. A linear equation in one variable is an equation equivalent in form to ax plus b is equal to 0. It doesn't have to be exactly that form, but it needs to be equivalent to that form, where a and b are real numbers, and the big one is that a cannot equal 0. What makes it a linear equation is that you have a variable to the first power, and that's the highest degree that you have for that variable. You don't have a square, you don't have a third, you don't have a fourth. You just have x to the 1. It doesn't have to be x. It could be like t to the 1, n to the 1, anything like that. I think those are the ones you'll see in the homework, actually. I went through the homework last night. So. Any questions on that? If a was 0, then it would just be b equals 0. Like nothing, right? All right, so linear equations are useful in many different situations, and I'm talking about in real world situations as well as in math. Or how to solve linear equations. So one method, and the method that I'm going to talk about for solving an equation, is to replace the original equation by a succession of equivalent equations. Equations having the same solution set until an equation with an obvious solution is obtained. And what that is saying is that when we had our equation like that, 65.52 plus 0.16x is equal to 70, and we did that operation of subtracting 65.52, we did it to both sides of the equal sign. And so what we end up with after, I believe it was 0.16 is equal to 4.48, is an equivalent equation to what we just had, what we began with. Okay? The way to know that we are ending up with an equivalent equation is that we have to preserve the relationship between the sides of the equation. This is the left-hand side, this is the right-hand side. We want to preserve the fact that they're equivalent, that they're equal. And how do I do that? Anybody know? By doing the same operation to both sides. Okay, if I subtracted 65.52 from this side but didn't subtract it from this side, this is no longer equal. Okay, and so that's what we're talking about when we're talking about finding equivalent equations, is that we're doing the same operation to both sides, so that way it retains its equality relationship between the two sides of the equation. Okay, and that's what the whole thing is. For any equation and inequalities when we get to that. Okay, so here are some things that you can do to retain an equivalent equation. You can swap your sides. If you have 3 is equal to x, you can make x is equal to 3. I do that a lot because I like having the x on the left-hand side. Well, not just the x, but the variable. So I'll do that sometimes. The other thing that we can do is we could simplify each side. So here I have x plus 2 plus 6 is equal to 2x plus 1. I can combine the 2 and the 6, make that x plus 8. And here I combine the 2x and the x, make it 3x plus 1. So I can simplify the stuff on each side. Since these are equal to each other, I know that those are equal to each other. Any questions on that? Okay, I could add or subtract the same expression to both sides of the equation. That's what we did earlier in the other one. So here we have 3x minus 5. They added 5 to both sides, which is going to end up resulting in 3x is equal to 9. So -5 and +5 will cancel. And the 4 plus 5 would be 9. Questions on that? Okay. You can multiply or divide both sides of the equation by the same non-zero. That's important. Non-zero expression. We don't want to divide by 0 because it's not defined. And so here, we have 3x over x minus 1 and 6x over x minus 1. We know from our domain studies earlier that x can't be 1 for that. But we can multiply both sides of that equation by x minus 1, which will reduce there, and we'll just be left with 3x is equal to 6. And then we could divide both sides of that by what? 3. And so x is equal to 2. Now, one of the big mistakes that people make for this, and I actually remember doing this on a test once, is that, what's it written? I think it was like 3x squared. No, it wasn't a 3, it was just x squared. X squared is equal to 9x, I think it's what it was, yeah. And I know we're talking about linears right now, but this kind of is something to remember not to do. Something you don't want to do is divide by x. Anybody can think why? Because as soon as I do that, I add caveat that x can't be 0. Okay, so if you can avoid dividing by x, unless you know that x is not 0 already, you don't want to do that. So avoid dividing by x if you can. Because we don't know if x is 0, and it says it needs to be the same non-zero expression. Oh, and this is a big one. If one side of the equation is 0, and we talked about this a little bit, I think yesterday. If one side of the equation is 0 and the other side can be factored, then we may use a zero product property. It's a really strong property, because if we have x times x minus 3 is equal to 0, one of those has to be 0. Because for the product to be 0, one of the terms being multiplied needs to be 0. So that means either x is equal to 0 or x minus 3 is equal to 0. We don't know which one, so we solve for either. And you hear me say the zero product property a ton of times, especially when we get to 1.2. Any questions on that? I think that's it for those. Yep. So here's my steps. Resolve the equation. And I'll kind of maybe elaborate on some of these. I think these are straight from the book. List any restrictions on the domain of the variable. So when you start, you look at the equation. Are there restrictions on the domain of the variable? You want to write those out, because when we're working through our equivalent equations, we may lose those as we go along the way. Okay, they may be equivalent equations, but we may lose some of those domain things we're looking at. And an example of that is that when we're looking at here, we started with these x minus 1s in the denominator, and so we knew x can't equal 1, but when we got here, that was totally gone, right? So there's no way for me to backtrace that. So you should always look at the beginning equation and make note of what your domain restrictions are. Step 2, simplify the equation by replacing the original equation with the equivalent equations using the procedures listed earlier. What we want to do is we want to get all the variables that we're trying to solve for on one side, everything without that variable on the other side, and then what we want to do is isolate the variable. We want to get the variable by itself, a singular x, a singular t, a singular n, or whatever we're looking for. Okay. Step 3, if the result of step 2 is a product of factors equal to 0, use the zero product property. So if you end up with something times something equal to 0, zero product problem. And step 4, check your solutions. How do we check our solutions when we solve an equation? We plug it into what? The original equation. Go all the way back, make sure. That'll also help with the domain stuff, because if you get a problem when you're doing that, you'll probably say, oh, well, looks like we have a domain issue. So it's a good idea to do that. Check your solutions. There are some problems later on, 1.5, I think, where you have to check our solutions, because some of them are extraneous solutions. They're solutions to the equivalent equations we found, but not the original equation. And so that is a case that arises. Checking all your problems is not a bad thing to do. Doesn't take long usually. It's usually a recommendation, I would say. All right. Any questions on those steps? Cool. So let's work out this problem. And we're going to start off with some simple ones, and it may be, you know, kind of elementary to some of y'all, but we're going to build that. So we're starting with this equation. They're telling us that 3x minus 5 is equal to 4. We want to solve it, figure out what x makes that true. What value or values of x makes that true. And so, like I said before, first thing we should do, are there domain restrictions? Is there a variable under, always messed up. Is there a variable in the denominator? There's no denominator here, so no. Is there a variable in our even root? There's no even root here, so no. So we don't have any domain restrictions that we know of for x. Let's move forward. This term right here has an x in it, the variable we're trying to solve for. This term does not, this term does not. So I want to move everything without an x in it to one side, everything with an x to the other side. Just a quick thing, I'm going to call this the left-hand side and this the right-hand side, so that way you know what I'm talking about. It's a little bit easier for me to talk about the problem that way. So, since the left-hand side has an x, right-hand side does not, I'm going to move the term without an x to the right-hand side. And I kind of got ahead of myself. I want to move this 5. How do I move that 5? We're going to add it. Why are we adding it? Yeah, so on the left-hand side, it's minus 5. If I add 5, that's going to cancel out, be 0. So you would do the opposite operation that's currently going on. And so we will end up with an equivalent equation of 3x. So let's actually write out what's happening. It's minus 5. And you don't have to do this every time. I'm just going to do it this time. Is equal to 4 plus 5. And so we can see the minus 5 plus 5, that's going to cancel out. 4 plus 5 is going to be 9, and so we end up with 3x is equal to 9. I think this problem was in the steps. Any questions on that? All right, so I got all my x's on the left-hand side. Oh, left-hand side for y'all here. I got all the non-x having terms on the right-hand side. What am I going to do to solve for x? This is what I'm talking about with isolate the x, right? Right now it's 3 x's. I just want 1 x, isolated alone. This is a multiplication happening here. So if I want to move that 3, what do I need to do? Divide. So I'm going to divide both sides. Whatever I do to one side, I need to do the other side to keep that equal relationship. 3 divided by 3 reduces. Just left with x is equal to 9 divided by 3 is 3. Questions on that process? So let's talk about what we did, and then we'll check our answer. But this is the equation we started with. This is an equivalent equation we came up with. This is another equivalent equation we came up with. And in this case, it has the x isolated, and it gives us the solution. To test our solution, to check it, we're going to do 3. We're going to substitute in our answer of 3, our solution of 3 for our x, and see if that works out. Now, 3 times 3 is 9. 9 minus 5 is 4. Does 4 equal 4? Yes, it does. That checks out. That's all you got. Just make sure you follow the order of operations when you do the check. And yeah, that's the main mistake that happens. Any questions on that? Here. All right, let's see what I got next. I think it's on the next page. All right. Now we got some fractions. So there's multiple ways to do this, to deal with it. You could distribute the 1/2. You know, take it, multiply it times the x, multiply it times the 5. That would be simplifying each side, but you end up with, and we're not going to do it this way, but I'm going to write out to show you. We end up with x over 2 plus 5 over 2 minus 4 equals, and then we distribute the 1/3. We'll end up with 2x over 3 minus 1/3, and now we got even more fractions, right? So let's not go that way. The other way that we could deal with this, and let me write out my problem real quick so I can work on it, is get rid of the fractions, right? I have the ability to multiply both sides of the equation, and it will stay equal, right? As long as I multiply both sides by the same number, it should remain equal. And if I multiplied this left-hand side by what? Would it get rid of the 1/2? A 2. And the reason being is that 1/2 times 2 is just equal to 1, right? If I wanted to get rid of the 1/3, what would I have to multiply by? 3. And that's because, give me a marker. 1/3 times 3 is equal to 1. Okay? But if I want to multiply both sides by the same thing, I can't multiply the left-hand side by 2 and the right-hand side by 3. My sides won't be equal anymore. Is there something I can multiply both sides by that'll get rid of both of those? A 6. And why a 6? Yeah, so 2 is divisible by 6, right? And 6, I wrote that wrong. I said it wrong. 6 is divisible by 2, and 6 is divisible by 3. So basically what we're trying to find is kind of what we did with the common denominator. We're trying to find the least common multiple of those denominators. And once you find what that is, you can multiply both sides by that number, and it'll get rid of your fractions. So that is the way that I say to do it. You know, you can do whatever you like. You can distribute the 1/2 and 1/3 and deal with it from there. But multiply it by the LCM of all your fractions. We'll get rid of them all, and you'll be done with it. The only issue is that we got to multiply it out. So I'm going to write it out. Remember, this is basically one term right here, right? All multiplication between them. This is another term, and then this side is just basically one term right here. So that means that my 6 is going to go to this term. So it's going to be 6 times 1/2 times x plus 5. It's also going to go to the minus 4. So we're going to have minus 6 times 4. Any questions on that? That's where the most mistakes happen, is people forget to distribute it. On the right-hand side, this is all just one term, so the 6 is just going to multiply to that. So it's going to be 6 times 1/3 times 2x times 1. And you may be able to do this in your head now, or you may be able to do it in your head when you get some more practice. You don't necessarily have to write this out every time. Like I say, and I'm just going step by step these first few times. So what's going to happen? The 6 times the 1/2. The 6 and the 2 are reduced. We're left with a what? A 3. 6 divided by 2 is 3, so we'll have 3 times x plus 5. We'll deal with that later. And then we have minus 6 times 4, which is 24. That's our left-hand side. Questions on that? All right, right-hand side. The 6 and the 3 were reduced. We'll be left with a what? 2. 2 times 1 is just 2. So we'll have 2 times 2x minus 1, which will distribute that next. Next, we're still going to keep simplifying our sides. I'm going to distribute 3 here. So 3 times x will give me 3x. 3 times 5 will give me 15. And still that minus 24 hanging out. You distribute the 2. 2 times the 2x will be 4x. And 2 times the negative 1 will be negative 2. Questions there? Still not ready to move stuff around. On the left-hand side, I still have a 15 minus a 24. That's going to be what? Negative 9. The 3x minus 9 will equal 4x minus 2. Okay, so we've got it into linear equation form now. I mean, it was at the beginning, but now it's in a simple form, right? So we can't combine anything. We can't simplify our sides anymore. We could factor them, but that's not going to do anything. Really, you don't want to factor unless one side is 0. We'll talk about that more in 1.2. And so what do we want to do? We got x terms on both sides. We got constant on both sides. Let's get all our x's on one side, all our constants on one side. We'll do it in steps, though. What do y'all want to do? There's a tons of things to do. I mean, there's a million, well, not a million. There's like 4 things we can do. You want to add the 9? All right, we can do that. So that's going to move that constant to the right-hand side. And so we'll be left with 3x is equal to 4x, what, plus 7? Now that has kind of put us into what our next move is going to be, which is going to be what? We want to subtract the 4x, right? We don't want to move the 3x because then the x will be on the same side as my constant. We want to move the x to the other side. So we want to subtract 4x on both sides. And so that's going to give us a negative x is equal to 7. Oh, that's good. I like how we got there. Cool. Because I would have avoided that. That's a good place to be. Well, if we know that negative x is equal to 7, what is x going to be? Or how do we find what x is going to be? Yeah, so there's 2 ways to do it. And the way that I usually do is I divide by -1. And so negative x divided by -1 is going to be x. A 7 divided by -1 is going to be -7. The other way to go about it, in case anyone's curious and maybe it makes more sense to you, is if we have negative x is equal to 7, we could multiply both sides by negative 1. It's really the same operation happening. Just different semantics, I guess. And so this is x is going to equal negative 7. Either way, we get the same answer. So I like doing a division thing.